the last line. Awesome. That last line of, if you have any doubt, please, include your questions in the chat box, is a wonderful line to start off with, because that is the premise of what we're going to talk about today. It's doubt in the structural viability of deteriorated and damaged concrete. And as it turns out, our next generation of junior engineers or engineers are coming into the construction and concrete industry at a really wild time. There is a mass exodus of civil engineers and concrete professionals happening right now. And when you get into your first job, and I really hope you get into concrete engineering, civil engineering, it's like a roller coaster, and there's always something exciting to deal with. And you can see that as proof with the order of the engineer ring that you get, and the story behind the order of the engineer ring. And BTW, as your generation says, I still wear my order of the engineer ring, and it's been 2 decades since I graduated college, or a little bit less than 2 decades since I first graduated college as a civil engineer. So today, what I wanted to talk about is a very basic approach to something that you'll have to deal with. And I say that in a way that I'm trying to put a little fear into your hearts. I like the idea of fear. I come from a generation, and I come from a background where fear was used as a motivation. And what you're looking at right now is a real structure that you can copy and paste throughout different parts of the world. And I'm sure even in Victoria, in this beautiful part of Canada that y'all live in, you can find bridges, locks, levees, spillways, concrete columns, I-beams, T-beams, one-way slabs, two-way slabs that look like this. And we're going to spend the majority of the presentation talking about this, and how you can use some of what you've already learned or what you have available, and you could take a class in, and that'll give you a job as soon as you graduate. That's one of the biggest concerns when you're a college kid, is all this work. Even if you're past college and you're in your job and you're not loving it, or you are loving it, but you want to see the future, what can I use that I learned in college to make a buck? Or what can I use that I learned in college that'll help me get to a more exciting portion of my career? And looking at this and figuring out if this catastrophic combination of concrete, rust, and seawater is going to stand up the test of time, to me, is exciting. And you are the superheroes who are standing in line to work with me on this. So, we've got an hour. I'm not going to use all of it to talk, and you're going to get to have a version of this presentation to look at. You can challenge me on concepts. Oh, I don't mind getting into arguments about concrete. One of my coworkers is on the phone, and we like to have no holds barred, folding chair conversations, like throwing things at each other about concrete and concrete design. So I don't care how challenging the question is. I love being challenged, and so should you. So we've already gone over my background, so we can go past that. I want to get into the purpose of this presentation. Then we're going to dive into the meat and the potatoes, or if you're a vegetarian, the portobello mushrooms and chili peppers. And that's looking at the basics. And the basics are the foundation on which we build our civilizations throughout time. Every society that we can look at and study, they make these awesome concrete or concrete-like structures using very basic technology. So we're going to start there, reviewing the basics. And I have a rudimentary drawing here. My favorite textbook for reinforced concrete is the Nolly 2009 edition. It reads like poetry, like Mark Twain, like Hobbit, or the Lord of the Rings. And it is an adventure every chapter. So after that, with the basics, and my assumption is kind of like what's his name did with that book, Einstein. If you've never read Einstein's general theory of relativity, In the foreword, Einstein says there is a certain assumption that I have that everybody participating in reading this literature, that you have a certain math level. So I'm making a certain assumption that everybody attending this has either a certain math or interest level that will engage them with the information we're about to share. And if you haven't taken reinforced concrete yet, don't worry about it. It's easy peasy mac and cheesy, and we're going to go over that today. Then we're going to look at that picture in more detail and start creating some or gathering some information to create our assumptions. And that'll lead us into our concrete beam analysis, because that's what we're going to do. We're going to take that big structure and we're going to say, hey, what's the most important part? And that's where we're going to start. We're going to do what engineers do, which is take something really difficult, make a whole bunch of assumptions, and crack on with the basics that we've learned in school and on the job site. Then we'll wrap it up with concise conclusion and open up for any questions. Wonderful introduction. My name is Dr. Belkowitz. I flipping love concrete. I love engineering. We are concrete superheroes, and it couldn't have gotten into a better profession. And I'll tell you, you are getting into the concrete industry at a very, very exciting time. There are major changes going on. And if you got questions for me on the science and engineering side afterwards about careers, or if you have questions on the practical manufacturing side, there's a guy named Matt McCombs over here who's been making concrete since I had a full head of hair and before that. And he can answer a lot of your questions about getting into the concrete industry as a career. So we got a lot of resources for y'all. Let's dive into this presentation. So this is a 1-hour webinar that I wanted to put on. And we do this a lot. I work with a lot of universities. I've been an adjunct professor. And where I come in is that I've spent not just a lot of time at the university level, which I love going to school. Nobody can talk. My mother calls me the perpetual student. And I intend to go back to school for another PhD and then a postdoctorate. That's how much I love school. But even more than that, I love applying what I've learned in school to the quote unquote real world. And I've had the privilege, nay, the pleasure of dealing with the bookcrete, labcrete, and realcrete all in one job site. And then getting that stuff out to the ASTMs, ACIs, and making it global concrete and outer planetary concrete, which is an awesome story, not for today. But anyway, so today we've got a 1-hour webinar that introduces y'all to the concept of applying your basic techniques to analyze the failed concrete structure. The ultimate objective of this webinar is to review how the degradation of concrete, reinforced concrete, impacts stress concentration, allowable load, and the running room of the following concrete structure. You know, at Intelligent Concrete, we have every year, or we used to have, we shut it down like during COVID, and Matt is going to help me bring it back to life. But we have this book writing competition where we pay our employees to write a book, and then we have guest editors come in who edit it, who put it through its paces, and they tell us which of the favorite book they have. Then, you know, the winner gets a $200 gift card, and we publish the book for our employees. And years ago, we had our professional engineer and one of our material scientists write a book on the ABCs of epic concrete failures. As it turns out, when a concrete structure fails, because most people don't care about concrete until something goes wrong. We all know concrete cracks. Asphalt can crack, but you never hear anything about it. But once you get a hairline crack in concrete, everybody's got their hands up screaming and huffing and puffing. But as it turns out, the reason why we huff and puff about concrete cracks is the wrong type of concrete crack can mean catastrophic failure. And that normally means lives lost. So, you know, not to bring a somber and serious tone to this, but you have the capacity, the tools in your toolbox right now to go out to the real world, concrete construction world, the make money world outside the academic institution right now. You just don't realize it. So let's dive into that. Let's review the basics and discuss the design process for a reinforced concrete beam. And the reason why I want to do that, the thing that I like to do is break everything down to its basics. And I said before we started, and for the professors on there, you can't yell at me because I said in the beginning that we are going to make a lot of assumptions. Now, there are some advanced techniques, and there is an advanced reinforced concrete class that you can take at different universities that will go into a lot more detail than what we're going to go into today. What we're going to talk about today is almost like, determining the loads for a multi-story home, right? I don't know if it was a Chinese or a Japanese concept that you treat it like rain loads, that you have to follow the loads as if rain was coming down the roof and the loads were trickling down the house. And we're going to do that too with this drawing right here that we had a really intense picture to look at. And it was almost so intense that it's one of those story problems that you get on a test that it's so intense, or your PE exam, if you're going to be here in the States, it's so intense that you're like, where do I even start? So as the expert here, I'm going to make the decision. And where I would start with this menagerie, with this spider web of issues, is at one of the most basic parts. I'm going to start at the beam, because from the picture, and we'll go back to in a second here, the beam to me is what is going to have the greatest impact on my entire system. My entire system here, it might not be a one-way slab in that photo, it might be a two-way slab, but it's a slab sitting on a series of beams, and those beams are sitting on columns. And when we take a really gross look at that picture again, you'll notice that the columns have some type of ties on them. They've had some type of patching work. And the slab, well, the slab looks nasty, but it's not as nasty as the beams. Especially when you take a look at some of those beams and see what's falling off of those beams, your heart might jump like I did when I first saw this photo. So what I want you to also ask is, you've already asked, excuse me, how do the individual's reinforced concrete parts make up the entire system? So like a rain load on a house or on a roof, when we have a jetty, a wharf, a bridge deck, or a bridge, we have the main load sits on top of the deck. The load is then transferred through tributary area to our beams, and the beams transfer that to our column. So we're going to block off our beam and just look at our beam, making an assumption that the load carried by that beam is a linear foot or a linear meter of our tributary area. Now, with that, making that assumption that we're only looking at our beam, we know that if our beam cannot sustain the original load, and if we lose the certain tension side of our beam, bad things will happen when we reach a failure condition. So what we want to do is develop a fundamental approach to evaluate these engineering specifications that we care about. Okay, so we originally said we're looking at a beam, and here is our beam. We have a distributed load. In some cases, I guess it could be a point load, but again, our assumptions, we're assuming a distributed load over this entire beam. And for our sake, we're going to ignore double reinforcement. The compression reinforcement, I'm assuming that we took a sophomoric level or junior level reinforced concrete class. So we're going to ignore our compression steel just to make the calculations a little bit easier in our time frame. But again, it's still the concept that we can start with a given load that we're allowed to use. We can start off with, hey, we had this design for a certain type of failure based on the reduction of both concrete and steel, or steel and concrete. Where the heck are we in the survivability of this structure? Okay, so again, I'm making this really basic. So here's our cross section, excuse me. Hold on, I just gotta take a sip of tea here. Cross section of a single reinforced concrete section. The rectangle itself, we're going to assume is our concrete. The AS is our steel area, and we're going to use our basic dimensions. Our B for the base of our beam, our D from our depth of our most extreme fiber to the center of our area of steel, and then the H is for our height of our steel beam. And with that, we're going to assume the standard strain and stress distribution. Now, if you've never seen this representation before, it is one of my favorite engineering representations in the world because it was named after my wife, and it is called the Whitney stress block. Not that she stresses me out, because that is further from the truth than anything, but I just love that it's named after her. And basically, I'm going to squish this thing down for you, and your professors might throw things at me, but again, I like to make things as palatable as possible. And if you've seen this before, you're like, Dr. John, I have no flipping clue what I'm looking at. I'm cool with that. Don't have a flipping clue what we're looking at. Sorry, that was supposed to be a lot smoother than it was. What you need to understand from the series of arrows and diagrams and neutral axes and A's and betas is that there is a compression side of our beam and there is a tension side of our beam. As an engineer, to design a reinforced beam, you have got to make sure that the compression side is balanced by the tension side. Now, when I was in college, and bear in mind, I went to a lot of different colleges, but when I was in college, I went to the United States Air Force Academy for my first civil engineering degree, and I had a terrible, and if he's on the phone, I'm sorry, but it's the truth, Dr. No. You were a terrible reinforced concrete structure teacher. And I remember I asked him, Dr. No, Professor No, what happens if the beam is not balanced? And he said to me, John, if the equations aren't balanced, the structure flies off the paper. He said it as a joke. And for some reason, I couldn't get past that idea. The structure doesn't fly off the paper. And at a certain point in your career, nobody's going to check over your shoulder if you decide, not that you will, to cut corners, save on steel, and have an unbalanced equation. At a certain point in your career, when you become a CE3, people might not look over your shoulder and say, hey, you got to balance that equation. When the equations are not balanced, structures fail, and there's a chance that people can get hurt and die. And with concrete, as we found with the Surfside apartments, the condos here in America, the new Braunfels Dam, within the last 3 years, we've had a plethora, a wide variety of concrete structures failing because ultimately that balanced state is lost. Either we lose the tension side, which is what we're going to discuss today, or something happens to the compression side. So if you didn't understand those, that's fine. What you have to understand is that there needs to be a balanced state for us to do the right design. Now, when I say the right design, as engineers, our design, our method of design is not for an immortal or a 500-year life cycle. We actually design our reinforced concrete with failure in mind. And that is the craziest thing. Why would you design something to fail? And the answer is we want to be able to control how it fails. And the way we normally say it in the industry is running room. That if a structure is going to fail, we can see it fail and everybody can run off the structure. Now, when we use reinforced concrete, and this is in the NAWI text or whatever textbook that you're using, there's 3 different zones we design the concrete to fail in. The compression controlled zone to the tension controlled zone. Now, where we want everything to happen is in this tension controlled zone as much as possible. The closer we get to this compression control zone in failure, the more likely we have a catastrophic failure. And that means a failure without running room. Now, I already showed you this. We have to have a balanced state. So when you look at a concrete beam, and I'm sure your professors have done this, where they take a foam beam and they bend the foam beam in half and they make the foam beam smile. So you have a beam of foam and it's smiling, and they usually draw squares on it. And you can see that, you know what? I have a picture of this. Hold on, let me get to that picture. You can see that the top of the, ooh, there it is. Uh-oh, did I just mess that up? There it is. So the top of the beam, the squares are squishing, and the bottom of the beam, the squares are expanding. And what that tells us is the bottom of the beam is in compression, or excuse me, the top of the beam is in compression, the bottom of the beam is in tension. The bottom of the beam, the steel, takes on our tension load. The top of the beam takes on our compression load. When we lose our steel, when our tension zone fails, it doesn't mean the concrete ultimately falls into the ocean. The concrete can still be there, but ultimately, if we lose our tension zone, when the load to cause failure creates that failure scenario, we don't have a tension failure. The failure is monopolized by the concrete. And we all know concrete is horrible in tension. So the concrete cracks, there's no steel to take on that tension load, and we have that catastrophic failure. So we cannot rely on the top portion or the concrete portion of our beam to do what the steel can do. Not yet, anyway. There's some technologies. Anyway, that's a different conversation. Okay, I'm getting ahead of myself. So what we're going to focus on, one of the things that we're going to focus on is this chart. You're going to see this chart again when we talk about our failure scenarios. Now, as an engineer, civil engineer, if you go back to the Latin term, civil means of the people. So you are a problem solver, and you report to your customer are the people. Your family, your friends, your kids, your grandparents, even people you don't know or like. They depend on you. That's why we wear that ring on the working hand of our, or our pinky of our working hand, to remind us how important our job is. So not only do you have to make things safe, my kids would say, no duh, dad, but you also have to make things economical. You have to make them in a way that it's not the only structure that we're building. So when I say that we're designing things that we know are going to fail, it's not a gamble, it's not a chance. We know what you design, what is built is going to fail, and that's okay. We want it to fail in the way that is safe for the community and when we deem it's ready to fail. So when you hear a lot of people saying, oh, we're designing these 50-year bridges, these 100-year bridges, please bear in mind, they are designing it with failure in mind. It's just for some reason, they want to put it past their retirement date, so maybe nobody holds them accountable. I don't understand the reason. But what I say is, instead of building a bridge that lasts 100 years, because if you've never been to New York, or any other major city in the world that was built in the 1800s or 1900s, my least favorite city to go to is Hoboken, New Jersey. Hoboken, New Jersey, which is right across the Hudson from Manhattan, was really built in the 1920s. It has the oldest train station in America. It's called the Lackawanna train station. Those roads, those bridges, those interchanges, they were built in the 1920s. It's 100 years later. It takes an hour to drive 1 mile in Hoboken, New Jersey, to go from one end of Hoboken to the next on Main Street. It's just terrible when you drive on a road that's over 100 years old. So instead of saying building a bridge that lasts 100 years, I'd rather build a bridge that lasts 30 years with as little maintenance. And then at the end of the 30 years, I can decide if I want to keep it or tear it down. So as an engineer, not only do we have to make these decisions about saving people, but we have to make long-term decisions. And let me impress upon you again, I'm not saying these things because somebody is paying me. Nobody's paying me to do this presentation, and nobody paid me to write this presentation. I'm doing this is because we are in a deficit of good engineers all over the world and off planet. And when I say off planet, Matt and I are lucky enough that we get to work on the moon and Mars. You know, to say I'm an expert in the United States, yeah, maybe 10 years ago, I am one of the concrete experts in our known universe, and my plan is to get to the unknown universe too. You are the next the next line of superheroes. So if it hasn't been impressed upon you yet, everything you learned about is just the beginning. If you want to start making real money tomorrow, get passionate, just like I am, about concrete and start getting into the information so you can start making these decisions with structures that are dying. The consequences for our structures failing is normally death. Rarely is it just, oh, money lost. New Braunfels, Texas, 2 years ago, we had a dam fail, and it was a bunch of rich people losing their front lawns. Blessed be. Isn't that a wonderful thing? The most recent time we've had a concrete structure fail in the United States, I believe it was 120 people that died. Real decisions, people. You're not kids anymore. And if you're about to graduate, you're about to get into an industry that desperately needs you. All right. So with that in mind, those motivated juices that I'm excited to learn about concrete, let's get into reviewing the failed structure. Remember, you're a superhero. So now you've got to have eyes like nobody else. You've got to see things that your common layperson, your English major, your human studies major is not going to see, because everybody can see that's a scary looking concrete deck. That doesn't look good. But I've already given you some hints. What information do we need? Well, first we need the original beam design. Why? Because I said that beam was the most important part. I said that the columns didn't look too bad. If you look in the back, some of the columns have some wraps on them. Oops. Some of the columns have some patchwork on them. And the decking itself, if you can look between some of the I-beams, the decking looks intact. If I have to complain about something, you can already hear the octave of my voice increasing. It looks like whatever the original beam size was, it has changed. There are literal sections of this beam, this reinforced beam, where the steel, can everybody see that piece of steel in the background that's falling off? Let me see if I can get a pointer. I don't think I can get a pointer on here. Here we go. Highlighter, laser pointer. Here we go. Laser pointer. Look at that. Can you see my laser pointer? There's a piece of steel falling off the reinforced concrete beam, and there's another piece of steel. And then there's another piece of steel. And this is not coming from the top of the concrete. This is coming from what I said was one of the most important pieces of this structure, these beams that we've got. So a lot of important information to know before we start is, what type of steel did we start with? How much steel? What was the concrete that we started with? And from here, what are the local location of the major failure points? Now, you could take the different sized beams. There's some girders in there. I don't care where you start, but start with something, and then you can go to another piece of the structure. Okay, so from the original placement, I'm going to give you some information. The strength of the concrete was designed to be 27.6 MPa. For our English-speaking folks or Americans here, that's 4,000 PSI at 28 days. It was designed as an air-entrained concrete, and yeah, sure, we're going to say that it had a little bit of silica fume in there, 5% silica fume. That really doesn't matter at this point. And oftentimes when you design with reinforced concrete, you know, that question of how much silica fume, how much air entrainment is not in there. But that is something as junior engineers, as future engineers, you'll need to know. Our steel starts off with a yield strength of 414 MPa, that's 60,000 PSI, and our modulus elasticity is going to be 200 gigapascals. The age of our structure is 20 years. And remember, we're assuming that this beam that we're going to now analyze is only single reinforced, and we're doing that for the sake of time. So again, this is just reviewing the basic. Here we have a single reinforced concrete beam. Its base is 305 millimeters. Its height is 508 millimeters. The depth from the extreme fiber to the center of the steel is 445 millimeters with 4 number 9 bars. I believe in Canadian, that's like a number 29 or number 39 bar. but the area of steel is 25.8 centimeters squared. The purpose of our project, and I just wanted to reinforce it, no pun intended. Man, this is a tough room. Not even a crack of a smile. What is the allowable load? This is not the factored allowable load. We're just going to look at the allowable load with a reduction in steel. The second thing that we want to ask is, does the beam design still fall within the acceptable failure region? And I think I explained why that's so gosh darn important. But again, it's not just the amount of load that the concrete can hold. It's also how it fails when it gets to that failure point. Because I'm okay with the reduction in load, but I'm not okay with compression controlled failure, which is that brittle catastrophic like failure. So part of the assumptions that we have leads into the solution of our query. The sections that failed, we already said it. It's not in the columns, it's not in the decking, it's not in the top of the beam. It's at the bottom portion of the beam where we have lost our concrete cover ad nauseum. Some of the steel has obviously deteriorated, taking our yield strength from what was 60,000 or 414 MPa to something much lower than it is today. And then, of course, the harsh reality that our steel is gone. Like, even if it was more than one layer of steel, I don't care. Your original design is gone. Matt and I get to visit the continental United States, as well as over the Big Blue Pond, as well as into Canada and Mexico. And we work with municipal and federal engineers, and your professors have, I'm sure, talked to some of them, who have to, and these are not my words, take these structures that we're analyzing right now and hobble them along until they can afford to pull them down. What some engineers have started doing is putting band-aids on these concrete bridges, infrastructure to bridges, so that when it does fail, it fails a lot slower, that it's a controlled flat failure, like carbon reinforced wraps, right? They put this carbon fiber band-aid on top of the concrete, and then they paint that carbon fiber wrap. So when it starts falling and failing, they can see it and they can close the bridge. What we're dealing with here is something that has not been maintained in the slightest. So we have to ask ourselves as engineers, do we recommend that we shut this structure down, or we keep it open and hobble it along as is? And with the red zone right here, that concrete cover failure, that steel deterioration, that steel fallout, we're about to find out that it's taking a lot of lives in your hand when you make these decisions. So I wanted to zoom into this photo, and I want to thank the United States Army Corps of Engineers for sharing this photo with us, because this was a structure that was eventually taken out of service because of the conversation that we're having here. This is a structure that is no longer being used, but you had huge vehicles rolling over this. Vehicles that were more than 40,000 pounds. I can't remember what that's in kg, but a lot of kg. And as you can see, the sections of the failed beams, the girders, which are still reinforced concrete beams, are the bottom section where we have that running room side, that tension side. Like I said before, we lost our concrete cover, and you can see strands of steel as if it was Egyptian cotton. And you can see that steel not only deteriorated, that brown looking stuff, we call that the steel bleeding, but that's the breakdown of the pacification layer. Rust on steel is not bad. We like rust. Rust is a protective layer. What happens when you expose steel is we break down that pacification. It's called depacification of that protective layer, and the steel starts corroding. It's a vicious, vicious cycle until the steel fails. And as you can see here, we have not one piece of steel. That is a strand of steel that is holding up a group of steel rods, or steel bars, excuse me. So we have steel fallout. Okay. All right, so let's get into it. All right, so we're going to get into the math, and I'm going to take a deep dive into the math. I'm using the basic values that I gave you before. I apologize; these are not in Canadian here. I left these, with the last class that I took or taught, excuse me. But what we're dealing with here is the idea of the yielding of steel and computing the allowable load. And the yielding of steel, if we go back to our yielding chart and our zone of failure, with the beam that we have, we find that our A yields 5.88 inches. And I'm taking my area of steel, multiplying it by the yield strength of the steel, and dividing it by this correction factor, the strength of the concrete at 28 days, and the base of our beam. And what that gives us is the depth of our compression zone. And I hate to scooch back through all these images, but again, remember that my favorite type of concrete engineering figure is the Whitney stress block. Well, the depth of that compression zone of our concrete that has to be balanced by the tension zone of our steel is that letter A. Now, to convert that letter A, the depth of my Whitney stress block, to the depth from my extreme fiber to our neutral axis, which is part of my yielding equation, I got to divide that by a correction factor, this beta 1, which is determined from our concrete strength. And as it turns out, it's not a coincidence that I use 27.6 MPa or 4,000 PSI, because that gives us a beta of 0.85. It's very easy to use. So I divide 5.88 by beta by 0.85, and it gives me a depth to my neutral axis. And remember, we know that the neutral axis, if you go back to that figure, there is no load applied or no load acting on our neutral axis. And again, that's part of our steel yielding equation. We get a C to our neutral axis of 6.92. Now I use that with the depth of my concrete from the extreme fiber to the center of my steel, that D, in my next equation right here, my steel yielding. And because we assume the single layer reinforcement, my E of S here, or my epsilon of S, is going to equal my epsilon of T. But we plug and chug those values, and starting off, we have an epsilon of S, a yielding of our concrete of 0.00459. And if we take that back to our chart right here, that green zone, this is where we're about. And remember, we want to be in our tension zone. We're okay with our transition. We're very happy in our, especially we're on the far side. We're on the tension controlled side of our transition zone. This is a great beam. I would be happy to drive over this beam with my 4 children. I'm very protective over my children. Now, furthermore, when we use that information to calculate our allowable load, our area of steel times the yield strength of steel times that depth minus the whole quantity, we get an allowable load of 291 kips per linear foot. Right, so every foot of that beam, we can hold 291 kips. That's where we're starting. That's when this thing was placed 20 years ago. Now, based on an assumed reduction in steel. And by the way, since I'm the professional, I get to say how much we assume. But if you want to challenge me and you're like, Dr. John, I don't like assuming that. I want to assume something else. I don't care. Go ahead, assume that number. Plug and chug. The equations are right here. They're not very hard to use. But let's say for a second, we reduce our area steel from 4 inches down to 1 inch. So easy to do that, because in a lot of situations in that photo, that is exactly what has happened. Well, first of all, our depth to our neutral axis changes. That means that, and I'm sorry, but I have to go back. When the depth to our neutral axis changes, that means our strain distribution changes. The way we had originally designed the beam to get a balanced state is all based on this. If the steel changes, then things are going to shift. So as you are students and as you are in the thick of this more than I do, the student will always spend more hours absorbing this information than the teacher. Never forget that. So when it comes to experts, you are the experts in the room. You spend more time than your professors. Yes, we teach you, and yes, I apply this in the operational world, but you know this figure more than most. And when I change this figure, when I change that one little letter, it's such a stupid letter. I mean, such a silly little lowercase letter. They didn't even want to give it an uppercase letter. But when you change that lowercase letter, that depth to the neutral axis, then that balanced state, it's no longer balanced. And the equations, they don't fly off the paper, neither do the figures. We're just taking people's lives in our hands. Okay, so let's get back to this. Man, it makes things sound so dramatic. Oh, this must be so exciting. So when we change the depth of our neutral axis and we plug and chug again, what we find is that load, the allowable load, changes from 291 kip feet down to 80 kip feet. And again, I'm not getting into the more advanced techniques, going into the gross area, the cracked area of our concrete. There are more advanced techniques which will get you more detailed information. But remember, as engineers, when we first started out, our first engineering class was on statics, right? And statics, you don't start out with reinforcement. You don't start out with tributary areas. You start out with the simply supported beam. And here we're taking it back to that simply supported beam. We're trying to make it as rudimentary as possible to drive home a point. You can get more detailed on the equations, but when it comes down to it, the basics show us where the concerns lie. And as it turns out, yeah, it's not good that we lose 80 kip or we lose 210 kip feet of allowable load for every linear foot of our concrete beam. But I remember I could deal with that. What I can't deal with is that our failure zone changes dramatically. When we lose 75% of our steel and we lose that balance, that stability, it's not the load that is concerned, it's the failure region. We go from this transition almost in the tension control, that true running room, to the point that we are in the depth of our compression controlled zone. That we are in a zone that when failure occurs, whether it's at 220 kip feet or at 80 kip feet, it is a catastrophic failure, and you will look people in the eyes as they run down the bridge for safety, and they will fall instantaneously. This is a lot of weight, and we have to be serious about how we prescribe what allowable limits a structure is allowed to use. And this right here, there is no doubt there is a reduction in service load. I mean, as a junior engineer with this loss of steel, it is almost a flinch. It is almost a knee-jerk reaction for you to say, well, obviously we can't put the tanks that we used to roll over this bridge. But the unbalancing, that was or the balancing, that was the origin of the design. That not only did it hold up that stuff, but if failure was going to occur, we can slowly get that tank. And yeah, we don't always roll tanks over, but it could be a VW bug. It was a proverbial straw that broke the camel's back. It wasn't a tank. And that's the biggest concern, the loss of running room, which leads to catastrophic failure. And it normally happens on a Friday afternoon during rush hour. It doesn't happen when there's nobody on the bridge. And if it does happen, well, play the lottery that day. If it happens when nobody was on the bridge and it was one of your structures, you should also play the lottery. Donate that money too, because you got lucky. The basics that you've learned, you're going to need to apply them because these are real structures. These exist throughout the world. I don't care if you're in Freehold, New Jersey, or Abu Hawas, Africa, or Victoria, Canada. Sorry, I keep saying that wrong. Now, I want to open up the floor for questions. And I've been very, very serious and to the point about how important this information is. Please don't take that with, I'm a mean individual. I would love for you to ask. I don't know how much time we have. If you can't ask the questions now, send me those questions and I'll be more than happy to answer them in the future. We have a lot more information on our YouTube site, our YouTube channel. We also have concrete mix design calculators. At this point, I'd like to open up the floor for any questions.
Thank you, Dr. John. It was an excellent presentation, and it was with great passion. So I can say one thing, just on the lighter side, that your passion has not only been in reinforced concrete area, it has moved to your personal life also, with the Whitney stress block being taken personally also. But I know it's without the stress, the Whitney without the stress block. Thank you. I think we'll open up to some questions here. And I have two, but I'll first let the others discuss about
Absolutely.
that. So any questions from you? Also, once attending online, if you'll have anything, you can please raise questions now, or else we can also have something by email.
Yeah, my email is at the bottom of the thank you page. Come on, y'all. This is a good time to ask a professional that's been working in the,
There's a question
for 2 decades.
Yeah, I think.
Yeah, so hi, Doctor.
Hi.
I'm not sure if the question is going to be out of the scope of your expertise, but I was wondering about non-destructive equipment to assess. Let's say I want to just add some nanosilica concrete mix, and I want to just compare the corrosion rate if I expose that concrete in an environment against just regular concrete mix made out of ordinary Portland cement. So the non-destructive equipment that I want to use to test this nanosilica content, will it be the same, like the same of non-destructive tests that are,
let me answer that in a few different ways. And for those of you who don't know what nanosilica is, it is one of the coolest concrete chemicals in the world. And it's where I focused my master's, my PhD work, and I've done, I love this stuff. If you haven't looked into it, there's a lot of great information. But to test the corrosion potential of concrete structures in the field with and without, and I say it that way, with and without nanosilica or with and without any value-added performance material, there's a lot of different ways. One of my favorite ways is before the steel corrodes, because normally when you see steel corroding, that concrete structure is in a bad state. So there's a permeability test. They're non-destructive tests that I like to use. We just finished using one in Indiana with the Indiana Department of Transportation, and the test is called the German. It's spelled like German, but it's pronounced German water vapor test. And it's a metal cell that you basically staple onto the concrete, and you pressurize water from this cell into this concrete over like a 4-hour period. And it ultimately tells you the permeability index of that in-place concrete. And the reason why I love that is because normally when we're putting something like colloidal nanosilica or nanosilica into concrete, what we're ultimately trying to do is create a concrete that is denser, has less pores and cracks, and the connection between those pores and cracks, which is often referred to as percolation. So the best way to identify percolation is through some type of permeability test. And while I don't make any commission from the selling of that equipment, it's one of my favorite field pieces of equipment out there. And again, it's called the German, and I'm typing it water vapor test. So that's one test that you can use. And you did say non-destructive. Matt just went over to, it wasn't Matt, it was one of our other guys, John, just went over to Indiana, and they were using ground penetrating radar to look at steel placement. And in a way, I believe you can use GPR ultra or sonication or ultrasonics. And I believe Professor Lou from Purdue University is starting to get this type of technology out to the market, where you can use sonication, ultrasound, that's what I was trying to say, to determine the state of concrete corrosion and steel corrosion. You know, outside of that, you're kind of limited when you say non-destructive tests, especially when it comes to the new type of steels that they're coming out with. We just work, and I'll shut up here, I'll finish this in here in about 10 seconds. We just worked with New Jersey Department of Transportation, and Matt is actually hearing this for the first time. I apologize, Matt. This was a phone call a couple of days ago, where they are using a new type of steel that no longer has epoxy on it, but has been blended. The steel has been blended with, I can't remember if it was magnesium or alumina, but it basically becomes a non-corrosive, a different type of non-corrosive steel. The problem with this steel is that we can't use half cell potentials to evaluate whether or not it's corroding or not. So I don't want to go back to those other methods, those electrical methods to identify corrosion states, because you might not be able to use those in the near future. Did I answer your question?
Thank you very much.
No problem.
Dr. John, I had two questions. One is, today we are using the carbon steel for all applications, and
Right.
all our codes, whether it is the ACI code or maybe out here Canadian code, like in my home country, it's the Indian Standard Code. All are you can say are designed for a steel with a specific elastic modulus and
Right.
and maybe your ultimate strength. Now, if I have a steel with a high, like almost twice that of the steel which we are using presently, which is the Fe 415. So if I'm having a flexural strength twice of that of, tensile strength twice that of this steel, and if I have a modulus of elasticity which is quite low, can we design a concrete with that, or reinforced concrete with that steel?
Absolutely. You can design concrete with any type of steel. I mean, shoot, remember that the largest non-reinforced concrete structure in the world is over 2,700 years old and has survived 7 earthquakes. Now, I'm talking about the Roman Pantheon, which, you know, is not any of the major Toronto expressways in the Greater Toronto Area, or expressways in the Greater Toronto Area. And it is reinforced, but it's reinforced with reeds and hemp. It's not reinforced with steel. So absolutely, you can design with a steel that has a greater yield strength, a greater modulus, but please bear in mind that there always has to be that balanced state. I remember the last class that I taught on reinforced concrete was at Stevens Institute of Technology. And one of the homework questions that I asked was looking at the same requirements. How would the load requirements, how would the design of the reinforced beam change if my yield strength went from 60 KSI down to 40 KSI and then down to 20 KSI? So yeah, that is a real question in some parts of the world. Eventually, you'll need to start using, look at ACI. ACI has a new excellence center for researching and designing reinforced concrete with non-metallic reinforcement. And if you're interested in grant opportunities, I believe they have a solicitation open right now. Well, they will award you somewhere between 35 and 50,000 US to do more research on non-metallic reinforcement. Did I answer your question, sir?
Yeah, absolutely. And it was somewhere it was related to this grant itself, which we are working on. So
Oh, nice.
you mentioned it right.
Nice.
I had a second thing. Have you designed a concrete with UHPC, having a design?
Yeah. So
into consideration the strength of the fibers, of the micro steel fibers into your design?
oh yeah. We've been designing UHPCs for many years now. That's really where we got our first start. The reason why I'm so friendly with the U.S. Army Corps of Engineers is because we help them with a lot of their ultra high performance and high performance mixed designs that they use for blast absorbing. We've also worked with a lot of the major companies that are throughout Canada and the US on scaling their UHPC mixed designs. So when I say UHPC, we've done everything from, let me just do the conversion, 241 MPa down to, your HPC, which is 103 MPa. And those properties, the compression as well as the tensile strength with steel fibers, the nasty steel fibers, as well as the pretty steel fibers, we had to get those properties within 12 hours to 24 hours or 28 days. So yeah, absolutely. We've not only designed with that stuff, but we've also designed the formulas that get you those properties. Did I answer your question?
Yes, thanks a lot. Thank you, Dr. John. I think it answered. You have something? Oh, yes. I think we don't have any more questions from the audience as well. So I'll request Maria. Yes, sorry. So sorry.
I had one more comment. As an engineer or as a junior engineer that doesn't have their PNs yet or their PE stamp, you can make upwards of 80 to 100,000 US doing this type of job. Okay. So there's a lot of potential out there in the industry to make some good money doing this. But if you have any other questions, I do have one more question. How do I get a copy of this recording?
Okay. Yeah, I think we'll send a link to you. Maybe once I'll just download it. Maybe I'll compress the file and send it across to you.
Thank you so much, y'all. If you have any questions, don't hesitate to shoot me an email. Thank you so much for your time.
Thank you. And I think I'll request Mariam to close this session.
Yeah, I just want to hello, Dr. John.
Is there anything you need me to do?
Hi, Dr. John. I just want to thank you on behalf of our two clubs, ACI and CSE. Thanks for your time. We had the pleasure of having you for more than 2 years, like for more than, I think, 3 presentations for our club. So thank you very much. I really appreciate it. And yeah, nothing else is remaining.
Thank you so much. Y'all have a great one. My pleasure.
Thank you. Bye.
Thank you.